Welcome back to our next video in our nuclear chemistry chapter. In this video, we'll talk about multi-step decay reactions. I mentioned in a previous video that sometimes a radionuclide will have to undergo multiple steps in order to become a stable isotope. And so we're starting with a uranium series in this slide. You can see here that it's showing multiple steps. So every arrow that is shown in this graph is showing a different type of decay step. The ones that are the purple downward sloping arrows are the alpha decay. The green rightward facing arrows show beta decay. So in this graph, we are again showing the number of protons on the x-axis, but now we're showing the mass number, the total mass number on the y-axis. So uranium, our starting point is actually uranium-238. And so what this graph is showing is as the uranium first decays by alpha decay, then we produce its daughter nuclide. That daughter nuclide will then undergo a decay reaction. And so you can see in here, if we count up all of our arrows, we have a total of 1, 2, 3, 4, 5, 6, 7, 8 alpha decays, 8 purple arrows, and then we have a total of 6 beta decays. And so instead of having to write a total of 14 separate reactions, we can actually put all of these reactions together in one equation. And so what's more common is this first example, we're showing the multiple steps that are happening. In this reaction, we can still predict our daughter nuclide. Now we just have to do a little bit more math. So realize when we have a coefficient in front of a nuclear particle, what we're going to do is actually multiply its value times the atomic number and mass number. So we're still balancing the same way, but now in order to get the total, we have to multiply a coefficient through. So in other words, for our alpha decay here, we have a total of 16 protons that are contributing, and then we have a mass number of 32 once we multiply those two numbers together. For our beta decay, we have a total of a -6, again watching our sign because the beta particle is negatively charged. We have -6 for our proton count, and we have a 0 for our mass number. What I'll encourage you to do is to pause the video and then work through these 3 problems. Once you have your solution to it, play it again, and I'll resume with the answers. Okay, so I assume that you paused to come up with answers. What you should have figured out, hopefully you saw, I'm going to change colors here for our pen. Hopefully you determined that for our first reaction, never mind, not changing colors. There we go. All right. For our first reaction, we are actually producing lead. We get an atomic number of 82, and we get a mass number of 206. For this second reaction, this is an example of nuclear transmutation. So this is, remember, one of the examples or the type of reaction where we produce new elements. And when I say we, I mean not me. Scientists who are working on these reactions. So one of the most recently discovered elements was actually carried out using this reaction. They bombarded CF, again, our little quiz here, that is californium, with, of course, we know calcium. So those two isotopes were bombarded together to make one of our newest elements. So you would predict a hopefully very high atomic number. And in fact, this one produced element number 118. So if you check your periodic table, that is actually the very last one in row 7. And this one has a mass number of 294. That element has now been named. So interesting little side note I like to tell students here is that the naming process is actually a political process for elements now. It used to be that whoever discovered an element got to name it, but now it's become such a collaborative process to discover new elements, that it has to go through a process, usually with a committee, although one of the more recent elements, I don't remember which one, but they actually open it up to the public to vote on a name. So if that ever comes out again, definitely vote. So anyway, the highest atomic number element that we know now is OG, and that stands for oganesson, named after a scientist who's works in Russia, has been a predominant player in the field of nuclear chemistry and developing new elements. All right, and then nuclear fission. I've mentioned this one before. This is the reaction that takes place in a nuclear power plant. So we're taking a uranium-235 isotope, bombard it with a neutron, and the goal is to, remember, fission is to break this down into two smaller elements. Usually fission reactions will produce some number of neutrons as a byproduct. That's what helps reactions continue going. And so hopefully you figured out, if you've worked this one, that our remaining atomic number is a 38. That means that we have produced the element strontium. And this specific isotope has a mass number of a 90. So hopefully you were able to come up with those products. And again, we often want to know the daughter nuclides in reactions, but the same principles apply. You could easily be asked to have to predict a parent nuclide. So make sure you understand how to predict elements on both sides of the equation and how to finish balancing. And just a reminder of how we know what types of reactions are going to occur. We use our band of stability here. And again, the black dots in this graph represent our stable isotopes. If I can get my pen to work, there we go. So the black dots that you see throughout this band of stability, the very dark dots are stable ones. Depending on where isotopes are relative to those black dots will determine the type of decay they undergo. And as a fun little side note here, of course, is our most recent version of the periodic table. These last few elements from 112 on, if you look at an older version of a periodic table, you'll notice that they don't actually have names included, if they're even included on the periodic table, because the names hadn't been conceived yet. So it took a while for a committee to come together to decide what those names would be. And of course, looking at those symbols, hard to tell what they are. And so a little extra slide for you that shows the names of element 110 through 118. So the name of it and then the atomic symbol. And so realize that a lot of names, the two primary resources that are used for naming are either a scientist. So as I mentioned, oganesson is named after a scientist, or after a location. So Tennessee, after Tennessee, and the nuclear lab that is there. What other one? Moscovium from Moscow, of course. Darmstadtium from Darmstadt, Germany. And others in here are named after scientists. Except for Livermorium, after the Livermore Research Lab. So, little interesting tidbit about the development and naming of new elements. And in our next video that we have, the next and last video that I'll be presenting for this chapter, we will get into the nuclear decay calculations that we perform for radioactive substances.